I want to talk about Antarctica. They are clearly protecting or preserving something that may or may not be under 3 miles of ice.
Antarctica was not always a frozen wasteland. 35 million years ago, it had forests, rivers, and a climate mild enough to walk across in a light jacket. Then something switched it off, and scientists spent 40 years arguing about what. Now they know, and the answer is terrifying, because the same gas that froze a continent is the one we are pumping back into the sky. So what turned a green continent into a sheet of ice? The green continent. It is hard to picture now, but Antarctica was once alive. During the Eocene epoch, roughly 50 to 34 million years ago, the continent that today kills everything that stays too long was covered in temperate forest. Rivers ran through valleys. Palms and southern beech trees grew in soil that is now buried under a mile of ice. Fossil leaves, pollen grains, and the bones of ancient animals have been pulled from the rock, and they tell the same story. This was not a wasteland. It was a habitat. Fossil pollen from the continent shows a landscape that would not look out of place in modern New Zealand, with temperate rainforests, ferns, and flowering plants covering what is now a desert of ice. Scientists have even found the fossilized remains of marsupials and large flightless birds that once lived and thrived in these ancient forests. The warmth was not subtle. Scientists have estimated that winter temperatures in some parts of Antarctica during the Eocene stayed above freezing, and that coastal waters reached temperatures you would associate with the Mediterranean today. Dinosaurs had walked this land tens of millions of years earlier, and their descendants, the birds and reptiles, were still here when the forests were. The continent sat over the South Pole, roughly where it sits now, but the climate was so mild that the pole position alone did not condemn it to ice. What mattered was the atmosphere, and the atmosphere was thick with greenhouse gases. Then, about 34 million years ago, the world lurched. Scientists call it the Eocene-Oligocene transition, and it is one of the most dramatic climate shifts in the entire fossil record. Global temperatures dropped by roughly 5 degrees Celsius in a geological blink. The forests of Antarctica died back to scrubby tundra, and then to nothing. Ice began to gather on the high ground, and it did not melt. It spread, and it kept spreading until nearly the entire continent was buried. The scale of what formed is difficult to hold in your head. The Antarctic ice sheet today covers more than 5 million square miles, roughly the combined area of the United States and Mexico. It holds about 7 million cubic miles of frozen water. If all of it melted, global sea levels would rise by roughly 190 feet, enough to drown every coastal city on Earth. 98% of the continent is buried. The other 2% is bare rock. It is the coldest, driest, windiest place on Earth, and nothing lives there except microbes and the scientists who visit in insulated stations. And for most of human history, nobody knew why it had happened. The freeze was obvious. The cause was not. So scientists did what scientists do. They argued for 40 years, and they built 2 completely different stories about what killed the green continent. So what were the 2 theories, and which one turned out to be right? The 40-year argument. The argument split into 2 camps, and both of them had evidence. The first camp pointed to carbon dioxide. We know from chemical signatures trapped in ancient ocean sediments that CO2 levels in the atmosphere were far higher during the Eocene than they are today, perhaps 3 or 4 times higher. To put that in perspective, today's level is around 420 parts per million, and it is already reshaping the climate. In the Eocene, it was well above 1,000. The world was a hothouse. We also know those levels began to fall. A Yale-led study published in the journal Science in 2011 showed that CO2 plunged by roughly 40% over a 3 million year period, right before and during the freezing of Antarctica. The idea was simple. Cross below a critical threshold of CO2, and the planet cools enough for ice to form at the poles. The second camp pointed to a map. 40 years ago, the textbook explanation was not about carbon dioxide at all. It was about tectonics. As the supercontinent Gondwana broke apart, Australia pulled away from Antarctica, and South America drifted away from the Antarctic Peninsula. This opened two deep water gateways, the Tasmanian Gateway and the Drake Passage, and allowed a powerful current, the Antarctic Circumpolar Current, to flow all the way around the continent for the first time. That current, the argument went, cut Antarctica off from the warm tropical waters that had kept it temperate. It thermally isolated the continent, the way opening a window in winter isolates a room from its heating. So, which was it? The gas or the gateway that killed the green continent? Both theories were elegant. Both had supporters. Both had evidence. And for 40 years, the argument ran, because neither side could fully disprove the other. It was one of the great unresolved debates in Earth science, and it mattered because understanding what froze Antarctica is understanding how sensitive our climate is to carbon dioxide. Then, in 2014, a team led by the climate scientist Matt Huber used a coupled ocean-atmosphere model to test both ideas head-to-head and published the results in Nature. Their conclusion flipped the story. CO2 decline, not gateway opening, caused the ice sheet to grow. The gateways may have helped draw CO2 down indirectly by changing ocean circulation and fertilizing plankton blooms that buried carbon on the sea floor. But the trigger was the gas, not the rock. Huber himself put it memorably. He said that as a society, we are dialing up the big red knob of carbon dioxide, and we are not moving continents around. The point was simple but devastating. It still holds. So if falling CO2 was the trigger and the whole planet was cooling, why did only one pole freeze? The mountains under the ice. The answer was hiding under the ice itself, and it took a study published in Science in 2026 to finally bring it to the surface. The study, led by the Earth scientist Thomas Gernon at the University of Southampton, traced a chain of events that began not 34 million years ago, but more than 160 million years ago, when Antarctica and Africa were still joined as part of the supercontinent Gondwana. The breakup of that supercontinent set in motion a series of events that would not culminate for over 100 million years, a slow fuse burning through deep time toward an icy detonation that would reshape the planet. When continents pull apart, hot material from deep inside the Earth, the mantle, rises beneath them. As it cools, it sinks again, creating slow, swirling movements that scientists call mantle waves. These waves travel beneath the continental crust over tens of millions of years, and they can do something remarkable. They can strip away heavy rock from the underside of a continent, making the land above lighter and causing it to rise, like a ship dropping cargo and floating higher in the water. That is exactly what happened under East Antarctica. Over more than 100 million years, mantle waves slowly lifted a vast region of the continent, creating a high plateau crowned by a mountain range called the Gamburtsev Mountains. Today, those mountains are completely buried under the ice sheet, their peaks rising to roughly 2,700 to 3,400 meters, comparable to the European Alps. They are named after the Soviet geophysicist Andrei Gamburtsev, who discovered them in 1958. Nobody has ever seen them. They were detected by ice-penetrating radar, and they remain one of the least understood mountain ranges on the planet. They are roughly the size of the Alps, and they sit in the dead center of the continent, as far from any coast as you can get on Earth, buried under more than 600 meters of solid ice. And their height is the whole point. For every 100 meters you climb in altitude, the air gets about 1 degree Celsius colder. Before the uplift, the Gamburtsev Mountains were simply too low. Snow that fell in winter melted in summer. But as the mantle waves pushed the land higher, the mountains eventually crossed a threshold of roughly 2 kilometers. Above that height, even in a world that was still 5 degrees warmer than today, snow could survive the summer and begin to accumulate as permanent ice. The first permanent snowfield on those mountains was the seed of an ice sheet that would eventually bury an area larger than the United States. And once it started, it could not be stopped. So what happened next turned that foothold into a continent killer. The chain reaction. What happened next was a chain reaction, and once it started, it could not be stopped. The first patch of permanent ice on the Gamburtsev Mountains did what ice always does. It reflected sunlight back into space instead of absorbing it. Scientists call this the ice albedo feedback, and it is one of the most powerful amplifiers in the climate system. It is the same reason the Arctic is warming faster than the rest of the planet today. When ice disappears, the dark water or rock underneath absorbs heat that the ice would have reflected, and the warming accelerates. The study's co-author, the climate physicist Philip Goodwin, estimated that this feedback alone lowered global temperatures by about 1 degree Celsius, but it triggered a second feedback at the same time. Cold air holds less water vapor than warm air, and water vapor is itself a greenhouse gas, a blanket that traps heat. As Antarctica cooled and the air above it dried, that insulating blanket thinned, and the temperature dropped further still. Together, these two feedbacks, the ice reflecting sunlight and the air losing its moisture, allowed the ice to spread from the mountains down across the plateau and eventually all the way to the coast. What had started as a thin skin of snow on a mountaintop became, over hundreds of thousands of years, a wall of ice, thousands of feet thick. By the time it reached the coast, the ice sheet was so heavy that it pressed the continental crust downward, creating the deep basins that still underlie West Antarctica today, more than 30 million years later. And there was one more link in the chain, discovered by a team at McGill University and published in Nature Geoscience. The opening of the Drake Passage did matter, but not in the way the old textbook theory claimed. It did not thermally isolate Antarctica with a wall of cold current. Instead, the deepening gateway reorganized ocean circulation in a way that redirected warm waters northward, increased rainfall on the continents, and accelerated a process called silicate weathering, in which rainwater slowly dissolves rocks and pulls carbon dioxide out of the atmosphere. The gateway did not freeze Antarctica directly. It helped drain the CO2 that did. So the old debate was never really CO2 versus gateways. It was CO2 helped by gateways, amplified by feedback, seeded by mountains. How many causes does it take to freeze a continent? The full chain was this. Gondwana broke apart. Mantle waves lifted the mountains. The gateway deepened and helped draw down CO2. The ice nucleated on the high ground, and then the feedback loops ran away with it. The result was the largest ice sheet on Earth. But if all of that was global, why did only one end of the planet freeze? Why the Arctic waited? Because the Arctic did not have mountains. This is the detail that ties the whole story together, and it is the part that the competing CO2-only theory could never explain. If falling carbon dioxide was the sole cause of the freeze, you would expect both poles to respond at roughly the same time. They did not. Antarctica gained a massive continental ice sheet about 34 million years ago. The Arctic stayed largely ice-free for another 20 to 25 million years. That gap, tens of millions of years of ice at one pole and none at the other, is one of the most striking asymmetries in the entire climate record, and it is the proof that elevation mattered. Thomas Gernon, the lead author of the 2026 study, put it plainly. If falling CO2 acted alone, you would expect the poles to respond symmetrically. Instead, Antarctica got a head start, and the reason was geological, not climatic. Antarctica had something the Arctic did not. It had high ground, lifted over 100 million years by mantle waves from deep inside the Earth. The Gamburtsev Mountains gave ice a place to nucleate, a cold platform where snow could survive even in a warm world, and from there, the feedback loops did the rest. The Arctic had no such platform. The North Pole sits over an ocean, and the surrounding land masses, what would eventually become Greenland, and the northern fringes of North America and Eurasia were low-lying. There was no 2-kilometer-high mountain range hiding under anything. For ice to form at the North Pole, the entire planet had to cool significantly more because there was no elevated terrain to give the ice its first foothold. It took another 20 to 25 million years of additional cooling and a further drop in CO2 before the Northern Hemisphere could assemble its own ice sheets. The Arctic's delay was not an accident. It was a consequence of geology, pure and simple. Without mountains to seed the ice, the North had to wait for the atmosphere to do all the work on its own, and that took millions of years longer. That asymmetry, a frozen south and a green north for tens of millions of years, is the fingerprint of the Gamburtsev Mountains. It proves that the freezing of Antarctica was not just about temperature. It was about history, about the deep geological past of a continent that had been lifted, grain by grain, over an almost unimaginable span of time. It was about elevation, about the shape of the land, about processes that started when the continents were still stitched together. And it raises a question that should keep you up at night. If CO2 crossing below a threshold froze Antarctica, what happens when we push it back above that threshold? So what is the terrifying part of this discovery? The terrifying part is that we already know how the story ends because we are writing the sequel in reverse. The Eocene-Oligocene transition happened because atmospheric CO2 fell below a critical level, estimated at roughly 600 to 700 parts per million. Below that line, ice could form and survive. Above it, the ice melted. The entire Antarctic ice sheet, all 7 million cubic miles of it, exists because of a carbon dioxide level that the planet crossed below 34 million years ago. Here is the problem. Before the Industrial Revolution, atmospheric CO2 sat at about 280 parts per million. Today, it is above 420, and it is rising every year. We are not yet back at the Eocene level, but we are moving in that direction faster than anything in the geological record, and we are doing it deliberately by burning the buried remains of ancient forests and pumping their carbon into the air. We are running the Eocene-Oligocene transition in reverse at a speed the planet has never seen. The threshold that froze Antarctica is not a distant, abstract number. It is a line on a graph that we are climbing toward, and the ice sheet that sits on the Gamburtsev Mountains is the proof of what happens when you cross it. The East Antarctic ice sheet is the largest on Earth. It stores enough frozen water to raise global sea levels by roughly 52 meters, or about 170 feet. It has survived for 34 million years because CO2 stayed low enough to sustain it. But the same feedback loops that built it, the ice albedo effect and the water vapor feedback, run in both directions. As CO2 rises and temperatures climb, the ice shrinks. The dark rock underneath absorbs more heat. The air holds more moisture, and the warming accelerates. The chain that froze Antarctica can unfreeze it. We know this because we have the geological evidence. We know what the world looked like the last time CO2 was this high and rising. Antarctica had forests. The last time carbon climbed this fast, there was no permanent ice at either pole, and sea levels were far higher. This is why the discovery is terrifying, and not in the vague, atmospheric way the word is usually used. It is terrifying in a specific, measurable, geological sense. We now know exactly what froze the continent, because scientists spent 40 years arguing about it and then published the answer in the two most prestigious journals on Earth. We know the gas, the threshold, the mountains, and the feedback loops. And we know that we are reversing the one link in the chain that we control. Nobody is moving the continents. Nobody is silencing the mantle waves. The only variable we are changing is the gas. Scientists finally discovered what froze Antarctica. Mantle waves lifted mountains. CO2 crossed below a threshold. Feedback loops turned a foothold of ice into a continent killer. And now we are pushing CO2 back up faster than anything in the geological record. The blueprint is sitting in a journal, and we are running it in reverse. Will the ice hold?